Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is a general physical law derived from empirical observations by what Isaac Newton called induction. In modern language, the law states, every point mass attracts every single other point mass by a force pointing along the line intersecting both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. The first test of Newton's theory of gravitation between masses in the laboratory was the Cavendish experiment conducted by the British scientist Henry Cavendish in 1798. It took place 111 years after the publication of Newton's Principia and 71 years after his death. Newton's law of gravitation resembles Coulomb's law of electrical forces, which is used to calculate the magnitude of electrical force arising between two charged bodies. Both are inverse square laws, where force is inversely proportional to the square of the distance between the bodies. Coulomb's law has the product of two charges in place of the product of the masses, and the electrostatic constant in place of the gravitational constant. Newton's law has since been superseded by Einstein's theory of general relativity, but it continues to be used as an excellent approximation of the effects of gravity in most applications. Relativity is required only when there is a need for extreme precision, or when dealing with very strong gravitational fields, such as those found near extremely massive and dense objects, or at very close distances. History. Early history. A recent assessment about the early history of the inverse square law is by the late 1660s. The assumption of an inverse proportion between gravity and the square of distance was rather common and had been advanced by a number of different people for different reasons. The same author does credit Hooke with a significant and even seminal contribution, but he treats Hooke's claim of priority on the inverse square point as uninteresting since several individuals besides Newton and Hooke had at least suggested it, and he points instead to the idea of compounding the celestial motions, and the conversion of Newton's thinking away from centrifugal and towards centripetal forces. Hooke's significant contributions. Plagiarism dispute. In 1686, when the first book of Newton's Principia was presented to the Royal Society, Robert Hooke accused Newton of plagiarism by claiming that he had taken from him the notion of the rule of the decrease of gravity being reciprocally as the squares of the distances from the center. At the same time, Hooke agreed that the demonstration of the curves generated thereby was wholly Newton's. In this way, the question arose as to what, if anything, Newton owed to Hooke. This is a subject extensively discussed since that time and on which some points, outlined below, continue to excite controversy. Hooke's work and claims. Robert Hooke published his ideas about the system of the world in the 1660s, when he read to the Royal Society on March 21, 1666, a paper on gravity, concerning the inflection of a direct motion into a curve by a supervening attractive principle, and he published him again in somewhat developed form in 1674, as an addition to an attempt to prove the motion of the Earth from observations. Hooke announced in 1674 that he planned to explain a system of the world differing in many particulars from any yet known, based on three suppositions: that all celestial bodies whatsoever have an attraction or gravitating power towards their own centers, and they do also attract all the other celestial bodies that are within the sphere of their activity; that all bodies whatsoever that are put into a direct and simple motion will also continue to move forward in a straight line, till they are by some other effectual powers deflected and bent, and that these attractive powers are so much the more powerful in operating, by how much the nearer the body wrought upon is to their own centers. Thus Hooke clearly postulated mutual attractions between the Sun and planets, in a way that increased with nearness to the attracting body. together with the principle of linear inertia. Hooke's statements up to 1674 made no mention, however, that an inverse square law applies or might apply to these attractions. Hooke's gravitation was also not yet universal, though it approached universality more closely than previous hypotheses. He also did not provide accompanying evidence or mathematical demonstration on the latter two aspects. Hooke himself stated in 1674, "Now what these several degrees of attraction are I have not yet experimentally verified, and as to his whole proposal, this I only hint at present, having myself many other things in hand which I would first complete, and therefore cannot so well attend it." It was later on, in writing on 6 January 1679, 80 to Newton, that Hooke communicated his supposition that the attraction always is in a duplicate proportion to the distance from the center reciprocal, and consequently that the velocity will be in a subduplicate proportion to the attraction and consequently, as Kepler supposes, reciprocal to the distance. Hooke's correspondence of 1679 to 1680 with Newton mentioned not only this inverse square supposition for the decline of attraction with increasing distance, but also, in Hooke's opening letter to Newton, of 24 November 1679, an approach of compounding the celestial motions of the planets of a direct motion by the tangent and an attractive motion towards the central body. Newton's work and claims. Newton, faced in May 1686 with Hooke's claim on the inverse square law, denied that Hooke was to be credited as author of the idea. Among the reasons, Newton recalled that the idea had been discussed with Sir Christopher Wren previous to Hooke's 1679 letter. Newton also pointed out and acknowledged prior work of others, including Bullialdus and Borelli. D.T. Whiteside has described the contribution to Newton's thinking that came from Borelli's book, a copy of which was in Newton's library at his death. Newton further defended his work by saying that had he first heard of the inverse square proportion from Hooke, he would still have some rights to it in view of his demonstrations of its accuracy. Hooke, without evidence in favor of this supposition, could only guess that the inverse square law was approximately valid at great distances from the center. According to Newton, while the Principia was still at pre-publication stage, there were so many a priori reasons to doubt the accuracy of the inverse square law that, without my demonstrations, to which Mr. Hooke is yet a stranger, it cannot be believed by a judicious philosopher to be anywhere accurate. This remark refers among other things to Newton's finding, supported by mathematical demonstration, that if the inverse square law applies to tiny particles, then even a large spherically symmetrical mass also attracts masses external to its surface, even close up, exactly as if all its own mass were concentrated at its center. Thus Newton gave a justification, otherwise lacking, for applying the inverse square law to large spherical planetary masses as if they were tiny particles. In addition, Newton had formulated in propositions 43 to 45 of Book 1, and associated sections of Book 3, a sensitive test of the accuracy of the inverse square law, in which he showed that only where the law of force is accurately as the inverse square of the distance will the directions of orientation of the planet's orbital ellipses stay constant as they are observed to do apart from small effects attributable to interplanetary perturbations. In regard to evidence that still survives of the earlier history, manuscripts written by Newton in the 1660s show that Newton himself had arrived by 1669 at proofs that in a circular case of planetary motion, endeavor to recede had an inverse square relation with distance from the center. After his 1679 to 1680 correspondence with Hooke, Newton adopted the language of inward or centripetal force. According to Newton's scholar J. Bruce Breckenridge. Although much has been made of the change in language and difference of point of view, as between centrifugal or centripetal forces, the actual computations and proofs remained the same either way. They also involved the combination of tangential and radial displacements, which Newton was making in the 1660s. The lesson offered by Hooke to Newton here, although significant, was one of perspective and did not change the analysis. This background shows there was basis for Newton to deny deriving the inverse square law from Hooke. Newton's acknowledgement, on the other hand, Newton did accept and acknowledge, in all editions of the Principia, that Hooke had separately appreciated the inverse square law in the solar system. Newton acknowledged Wren, Hooke and Halley in this connection in the Scholium to Proposition 4 in Book 1. Newton also acknowledged to Halley that his correspondence with Hooke in 1679–80 had reawakened his dormant interest in astronomical matters. But that did not mean, according to Newton, that Hooke had told Newton anything new or original. Yet am I not beholden to him for any light into that business, but only for the diversion he gave me from my other studies to think on these things, and for his dogmaticalness in writing as if he had found the motion in the ellipsis, which inclined me to try it. Modern controversy since the time of Newton and Hooke. Scholarly discussion has also touched on the question of whether Hooke's 1679 mention of compounding the motions provided Newton with something new and valuable, even though that was not a claim actually voiced by Hooke at the time. As described above, Newton's manuscripts of the 1660s do show him actually combining tangential motion with the effects of radially directed force or endeavor. For example, in his derivation of the inverse square relation for the circular case. They also show Newton clearly expressing the concept of linear inertia, for which he was indebted to Descartes' work, published in 1644. These matters do not appear to have been learned by Newton from Hooke. Nevertheless, a number of authors have had more to say about what Newton gained from Hooke, and some aspects remain controversial. The fact that most of Hooke's private papers had been destroyed or have disappeared does not help to establish the truth. Newton's role in relation to the inverse square law was not as it has sometimes been represented. He did not claim to think it up as a bare idea. What Newton did was to show how the inverse square law of attraction had many necessary mathematical connections with observable features of the motions of bodies in the solar system, and that they were related in such a way that the observational evidence and the mathematical demonstrations, taken together, gave reason to believe that the inverse square law was not just approximately true but exactly true. About 30 years after Newton's death in 1727, Alexis Clairaut, a mathematical astronomer eminent in his own right in the field of gravitational studies, wrote after reviewing what Hooke published, that one must not think that this idea of Hooke diminishes Newton's glory, and that the example of Hooke serves to show what a distance there is between a truth that is glimpsed and a truth that is demonstrated. Modern form. In modern language, the law states the following. Assuming SI units, F is measured in newtons, M1 and M2 in kilograms, R in meters, and the constant G is approximately equal to 69896674000000006.674 times 10⁻11 nm2 kilograms minus 2. The value of the constant G was first accurately determined from the results of the Cavendish experiment conducted by the British scientist Henry Cavendish in 1798. Although Cavendish did not himself calculate a numerical value for G, this experiment was also the first test of Newton's theory of gravitation between masses in the laboratory. It took place 111 years after the publication of Newton's Principia and 71 years after Newton's death. So none of Newton's calculations could use the value of G. Instead, he could only calculate a force relative to another force. Bodies with spatial extent. If the bodies in question have spatial extent, Then the gravitational force between them is calculated by summing the contributions of the notional point masses which constitutes the bodies. In the limit, as the component point masses become infinitely small, this entails integrating the force over the extents of the two bodies. In this way it can be shown that an object with a spherically symmetric distribution of mass exerts the same gravitational attraction on external bodies as if all the object's mass were concentrated at a point at its center. For points inside a spherically symmetric distribution of matter, Newton's shell theorem can be used to find the gravitational force. The theorem tells us how different parts of the mass distribution affect the gravitational force measured at a point located at distance r0 from the center of the mass distribution. The portion of the mass that is located at radii r less than r0 causes the same force at r0 as if all of the mass enclosed within a sphere of radius r0 was concentrated at the center of the mass distribution. The portion of the mass that is located at radii r greater than r0 exerts no net gravitational force at the distance r0 from the center. That is, the individual gravitational forces exerted by the elements of the sphere out there, on the point at r0, cancel each other out. As a consequence, for example, within a shell of uniform thickness and density there is no net gravitational acceleration anywhere within the hollow sphere. Furthermore, inside a uniform sphere the gravity increases linearly with the distance from the center. The increase due to the additional mass is 1.5 times the decrease due to the larger distance from the center. Thus, if a spherically symmetric body has a uniform core and a uniform mantle with a density that is less than 2/3 of that of the core, then the gravity initially decreases outwardly beyond the boundary, and if the sphere is large enough, further outward the gravity increases again, and eventually it exceeds the gravity at the core-mantle boundary. The gravity of the Earth may be highest at the core-mantle boundary. Vector form. Newton's law of universal gravitation can be written as a vector equation to account for the direction of the gravitational force as well as its magnitude. In this formula, quantities in bold represent vectors, where F12 is the force applied on object 2 due to object 1, g is the gravitational constant. M1 and M2 are respectively the masses of objects 1 and 2. R12 equals R2 minus R1 is the distance between objects 1 and 2, and is the unit vector from object 1 to 2. It can be seen that the vector form of the equation is the same as the scalar form given earlier, except that F is now a vector quantity, and the right-hand side is multiplied by the appropriate unit vector. Also, it can be seen that F12 equals minus F21. Gravitational field. The gravitational field is a vector field that describes the gravitational force which would be applied on an object in any given point in space, per unit mass. It is actually equal to the gravitational acceleration at that point. It is a generalization of the vector form, which becomes particularly useful if more than two objects are involved. For two objects, we simply write R instead of R12 and M instead of M2 and define the gravitational field G as, so that we can write. This formulation is dependent on the objects causing the field. The field has units of acceleration, in SI, this is meter per square second. Gravitational fields are also conservative, that is, the work done by gravity from one position to another is path independent. This has the consequence that there exists a gravitational potential field V such that if M1 is a point mass or the mass of a sphere with homogeneous mass distribution, the force field G outside the sphere is isotropic, i.e., depends only on the distance r from the center of the sphere. In that case, the gravitational field is on, inside and outside of symmetric masses. As per Gauss' law, field in a symmetric body can be found by the mathematical equation, where is a closed surface and is the mass enclosed by the surface.